Okay guys, so let's start with the new major topic in hydraulics. So this time we will now discuss the fluid flow in pipes. So alamin muna natin kung ano ba yung konsepto ng fluid flow in pipes. So let's just see here that we have a flow of a fluid from point A to point B. So guys, this is flowing in a medium. So this medium is also known as a wari na lang tuwid. So this is a conduit kung tawagin. Okay, so siguro familiar kayo sa word na conduit kasi ito ay same material lang din or same lang din ang tawag dun sa dinadaluyan ng current sa isang circuit. Okay, so gaya nga ng sabi ko sa inyo before, yung topic na yun sa circuits is halos kapareho lang din ng concept ng fluid flow and pipes. So meron tayong isang topic doon kung saan pag-aaralan natin yung series and parallel. So kung ano yung concept sa circuits, ganun-ganun lang din yung gagawin natin sa pipe. Okay, so ano ba yung definition natin for a conduit? So a conduit is a channel. So this is a channel for conveying a fluid, or pwede rin natin sabihin na gases, kasi ang gases is considered also as a fluid. Okay, pero most of the time naman is water din naman yung ginagamit natin. Isang magandang example dito is kapag nagdi-design tayo ng water distribution system. Okay, so ang point A natin is yung tinatawag natin na source, or dito nagsisimula yung tubig, and then yung point B, so that will be the point of discharge. Okay, so itong conduit na to is mahati sa dalawang category. So the first category will be a pipe. And the other one will be an open channel. So, alamin natin yung difference ng dalawang ito, ng pipe and open channel. Actually guys, yung open channel naman kasi, sometimes yung material na ginagamit sa kanila is pipe. Pero para lang din mas clear, alamin natin yung difference ng dalawa. Okay. So yan. So pipes, so when we consider pipes, so this is a closed conduit. Ibig sabihin yan, sarado siya. Pero yung open channel natin, sometimes, meron tayong mga open channel na closed conduit din. And meron yung tinatawag na open conduit. So, to make the story short, yung pipe natin is under pressure. Okay? Or, yung flow ng fluid sa kanya is punong-puno siya. Okay? So, lahat ng kanyang perimeter is basa. Unlike dito kay open channel, tandaan nyo na lang na ito is exposed sa atmosphere. So, yung mga open channel natin, that's like for example, for this one. So, we have a rectangular channel kung saan yung ibabaw niya is exposed to atmosphere. And sabi ko nga sa inyo, di ba, yung open channel kasi, pwede rin kasing gamitin dyan is yung mga RCP or reinforced concrete pipe, or sometimes known as culvert. Ayan. So, I believe na discuss ko naman to sa ating highway engineering. Okay. So, tandaan nyo na lang na kapag pipe, unlike dito sa pipe na closed conduit siya or fully basa yung kanyang perimeter. So, dito sa mga open channel, merong portion na hindi basa yung or ito is merong air. Okay? So, next, pressurized. So, for pipe, this is pressurized. So, itong pressure na to can come from pump para ma-pressurize siya, or ito yung tumutulong para yung tubig is maparating natin to different or malalayong location. And sometimes, mamaya doon sa sunod nating ipapakitang slide, elevated to. So yung height niya, so yung elevation head niya would produce pressure. Di ba alam naman natin sa paglalim niya or yung equation na gamma H, paglaki ng pressure. So ito is na-discuss siguro to sa soil mechanics and even in fluids. fluid. And next, for open channel, so this is depends on the slope. So dumedepende siya sa slope. So 'di ba sa drainage system naman natin, alam naman natin para tumakbo ang tubig niyan, naka-sloping or sloping kasi yung ano niya, pagle-lane ng mga RCP mo or even yung open channel. So dapat mas mataas yung mas mababa yung isang point considered sa entry point niya para dumalo yung tubig natin pababa. So papunta siya sa mga creek or any bodies of water or kung saan pwede mo i-retain yung tubig mo. And for pipes, one good example of this is yung water supply and distribution system. And for open channel, so ito nga yung sinasabi ko, sewerage and drainage system. So para mas maunawaan pa siya, ipakita natin siya or illustrate natin using these diagrams. Ayan. So, dumako muna tayo doon sa pipes. So, let's just say for example, meron ka ditong elevated water tank. So, yung elevation niya away from the ground level, so i-denote na lang natin siya as H. So, this H will produce a energy head para yung tubig is mapapunta natin dito sa mga household. So, maglatag tayo ng pipe or water distribution system and then supplyan natin itong mga bahay na to. Ito bahay to lagyan natin ng bintana. Okay. So, gagawa tayo ng water distribution system dyan. So, siguro gawa na lang tayo dito ng loop. Ayan. So, naglatag tayo dyan ng mga piping system. And then, ito. Yan. Itap natin siya dito. Okay. Yan. So, itong elevated water tank, so ang concept nga nito, so para magamit natin yung kanyang elevation head or yung H dun sa ating total energy equation. Yan. Ayan. Okay? So, para makatulong siya or may distribute niya yung tubig dito sa mga households natin. So, sometimes naman, gumagamit rin tayo ng pump or pump booster para para makatulong lang din dito sa pagdidistribute ng tubig do sa ano. So, because of this pump, ang nangyari dyan, do sa linya ng ating tubig is nagkaroon dito ng under pressure. Okay? So, yung loob niyan is pressurized or under pressure. So, ganun lang din naman yung konsepto niya kapag dating niya doon sa mismong bahay. Kung in-enlarge mo kasi siya, ito kasing water distribution system mo sa bahay is parang isang malaki lang na water distribution system in an urban area. Okay? So, nangyari lang dito sa second figure natin. So, dito meron kang laboratory, meron kang water closet, and meron kang shower area. And laboratory. Okay? So, ganun lang din yun. So, meron ka dito na water distribution system sa bahay kung saan ayan, may linya siya ng tubig, So, coming from this pump, ayun nga, sinupply ng tubig niya into another water distribution system sa loob ng bahay. Kumbaga, rin to, di ba? Sabi ko nga sa inyo, pwede mo rin illustrate or pwede mo rin ihilan tulad sa veins or ugat ng tao. Meron tayong mga major veins, meron tayong mga minor veins o yung maliliit na ugat. So, ganun lang din yung concept niya para masupplyan siya ng tubig. Kung sa katawan ng tao is dugo, dito naman is tubig. Okay? So, gaya dito, this is under pressure. So, under pressure or pressurized. Meanwhile, dito naman sa open channel, so, for example lang, itong mga household na to is dumating yung tag-ulan. So, habang umuulan yan, ayan. Ang nangyari dyan, so syempre pupunta sa bubong ng bahay. And then, ang nangyari dyan, meron nga tayo ng storm drainage system dito sa karsada. Usually, it is located in the sidewalk. Okay? So, ito mga roof drain mo, ayan, is nakatap lang din dito sa ating storm drainage system ng isang city or municipal. Okay? And if ang mangyayari dyan, meron ka dito mga inlet, ayan, yung mga pasukan ng tubig. And then dito, meron ka mga catch basin. Okay? And this will be discharged. So, ano natin? Yung mga factors na nakatulong para tumakbo ang tubig. So, di ba sloping siya dapat or coming from a high elevation? Paganyan siya. Okay, so para tumakbo lang yung tubig dun sa mga catch basin natin. Okay? So, same lang din sa loob ng bahay. So, eto, meron ka lang din dito na kung ito merong water distribution system. So, syempre, once na nagamit mo na yung tubig or yung used water, is tatakbo lang din siya dito. So, ito, meron din ito mga drain. So, maglagay tayo dito ng floor drain. And then dito sa shower area, lagay tayo dito ng shower drain. SD. So, ganun lang din yon. So, meron siyang labasan dito ng tubig. Mga naka-elbow pa yan. Ayan. So, I believe ito is na-discuss sa inyo sa plumbing design or BD2. So, alam ko, pinagawa kayo dito ng mga professor nyo ng plano, plumbing system design. The same time, yung water distribution design. Ayan. So, sloping lang din siya. So, para tumatakbo lang din yung tubig. So, ang takbo niyan to septic tank. Septic tank. Or sometimes, kung walang septic tank, diretso na siya sa mga tinatawag nating sewage treatment plant or STP. Okay, so I hope nagkaroon ng clear idea between the difference of pipes and open channel. So, tandaan na lang na yung pipes, fully basa yung perimeter ng pipes mo. Unlike kay open channel na merong portion siya na exposed sa atmosphere. And for pipes, it is pressurized open channel. Not pressurized. It is affected by the slope, gravity, and ayun nga. Okay, so under this, maka-categorize natin yung flow in pipes into two. So, we have this laminar flow. So, also synonymous to the word na calm or kalmado yung takbo ng tubig. So, describes a fluid motion that is smooth. And we have also the turbulent flow. So, pwede mo siyang ihalin tulad sa word na chaotic. Or nangyayari dito, so this describes a fluid motion that is eddying and unsteady, from which yung fluid particles transverse to the fluid's flow direction. Or nangyayari, nag-criss-cross na yung mga water particles or fluid particles sa isa't isa. Okay, so paano ba natin nakakategorize yung flow in pipes if it is under the category of laminar, or pwede rin nating sabihin na siya is under turbulent, and meron pa tayong pangatlong category. So, it is transitional flow. So, paano ba natin na-categorize yun? So, this can be categorized by performing the experiment, yung tinatawag nating Osborne-Reynolds experiment. So, I'm going to share you a video na nakita ko sa YouTube kung paano ba kinoconduct yung Osborne-Reynolds experiment. So, guys, please watch this next video.
In this video, we will be demonstrating the Osborne-Reynolds apparatus, the H215, which is part of Tech Equipment's fluid mechanics range. It is a freestanding piece of equipment for demonstrating the transition between laminar and turbulent flow and allows students to investigate Reynolds numbers. Historically, many engineers and scientists investigated the behaviour of flow in pipes, but it was British physicist named Osborne-Reynolds who first identified the variables controlling the flow and produced a rational means of predicting the nature of flow. Reynolds showed that the behaviour depends on the balance between inertia and viscous forces in the fluid. This led to the definition of a non-dimensional parameter now called Reynolds number, which expresses the ratio of inertia to viscous forces and can be used to identify the conditions under which the flow changes from laminar to turbulent. By experiment, it was found that the change always occurred at a similar value of Reynolds number, irrespective of the fluid and the size of pipe. At a low velocity, flow tends to be dominated by laminar flow, which looks like a sheet of fluid moving smoothly. At a high velocity, the layers of fluid are mixed up and turbulence occurs. This will churn up the flow, known as turbulent flow. The Osborne-Reynolds apparatus allows you to study the nature of the flow in a pipe by observing the behaviour of a filament of dye injected into the fluid. Let's take a look around the apparatus. As you can see, there is a precision bore glass pipe that is held vertically in a large stand that is open at the front with adjustable feet. At the top is a glass constant head tank. This holds water that passes into the main tube through this bell mouth entry here. The high-quality glass composition allows optimum viewing of flow behaviours. The water to this tank passes through a diffuser and stilling bed which contains glass beads. These together create a uniform flow as the water passes through it. The fixed overflow pipe here ensures there's a constant head of water which should be connected with a tube to a drain. The thermometer included measures the temperature of the water, which is required for some of the experiments. At the rear of the apparatus is a supply pipe that can be connected directly to a tap or to the outlet of the optional temperature control module. For normal demonstrations, a controlled supply of cold water can be used. To find the flow rate, you collect a known quantity of water in a measured time. To see the pattern of flow, i.e. laminar, turbulent and the in-between transition phase with intermittent pulses of turbulence in the pipe, you'll use a dye injector to inject a fine filament of dye into the top of the tube. The dye injector needs to be positioned as centrally as possible to get the best results. You can also use the optional heat module, the H215A, which is a separate freestanding unit for learning about the effect that the temperature of water has on its viscosity. For more information on the Osborne-Reynolds apparatus and other experiments in the fluid mechanics range, including the friction losses and pipe experiment and viscosity and particle drag experiment, click on the link in the description box below. Thank you for watching.
Okay, so to summarize yung napanood nyo kanina doon sa video na yun, so yung Osborne-Reynolds experiment is parang ganito lang yung konsepto niya. So dito meron kang bulb kung saan ito is ipipihit mo paunti-unti para mabuksan yung or mag-flow yung fluid dito sa loob ng pipe. Ngayon meron ka ditong dye or pangkulay sa tubig, ayan, from which it is controlled also by a separate bulb. Okay? So, ngayon, nang binuksan mo yung bulb mo, ayan. So, syempre, aagos yung tubig dyan. So, paunti-unti mo siyang bubuksan. So, binuksan mo lang siya ng dahan-dahan. So, anong nangyari? Nag-flow yung tubig mo dito. Okay? So, habang nag-flow siya dito, so, syempre, yung velocity niya is mabagal pa lang kasi hindi pa siya totally bukas. Ano? And then, ang nangyari, sunod, is unti-unti mo rin bubuksan yung inyong bulb dito para yung dye o yung kulay is unti-unti ring mag-discharge dito sa loob ng pipe. Ito is siya, embedded or nasa loob mismo siya ng pipe. So, ito is marirelease. So, since yung velocity mo is very fluent pa lang or mabagal pa lang, makikita mo dito, diba nakita nyo doon sa video, straight path pa lang yung takbo ng dye doon sa loob ng iyong pipe. Ngayon, as you turn yung habang binubuksan mo yung bukasan ng tubig or yung iyong bulb is gradually opened. So, ayan. So, mas binuksan mo pa siya. So, at the same time, again, eto, since nag-flowing na yung iyong dye dito sa iyong loob ng pipe, so anong nangyari? Siyempre, bumibilis na yung tubig mo. So, kung napansin nyo doon sa video, yung flow dito ng dye is unti-unti na siyang nagiging chaotic. So, nagkaaroon na siya ng surges sa flow. And then, once na itong valve na to is fully opened, so nangyari, ayan, sobrang bilis na ng velocity niya. So, pakita natin. So, less pa lang yung velocity niya dito. So, dito is increasing. And then, ito yung maximum. Okay? So, nangyari nga, yung dymo dito is, nag-crisscross na siya or parang humalo na siya totally do sa flow ng iyong tubig. So, this can be categorized as our turbulent. Kung ika-categorize nga natin. Dito, this is a transitional flow. And ito is a laminar. Okay? So, dito papasok yung concept ng Reynolds number. So, define muna natin Reynolds number. Again, ito naman is parang na-discuss ko na last time sa video lecture na provide ko. Pero mas laliman lang natin yung ating understanding for Reynolds number. So, again, Reynolds number is denoted by the symbol R sub E. So, take note of this. So, this is a dimensionless parameter. Okay? So, walang dimension siya. Or walang unit. So, this is characterized whether a fluid flow is laminar, turbulent, or transitional. So, the equation for the Reynolds number. So, ang sabi nga nito. So, this is just the ratio between the inertial forces and the viscous forces. So, ayan. So, this can be simplified using this equation. So, this is just the ratio between the inertial forces over the viscous forces. So, pwede natin siyang illustrate using this figure. So, let's just say, kuha tayo ng portion ugat ng pipe. Okay? So, in this pipe, meron tayong fluid flow. So, pumapasok yung tubig dito. Sabihin natin dyan. So, itong force na naproproduce ng fluid flow na yan, so ito yung tinatawag nating inertial forces. And from the properties ng iyong fluid particle, merong kasi tinatawag na viscous force. So, ito yung parang pumipigil dun sa pagdaloy ng tubig mo. Or kapag yung fluid particles mo is parang rin siya, frictional force. Yung fluid particles mo kasi is nag-iis-isan. Or nag-aanuhan sila between each other. So, for example na lang din, ayan nga, ito yung iyong fluid particles. So, sa boundary layer niyan, ito. Boundary layer. Sa boundary layer niyan, meron kasing inertial force. So, itong inertial force, pwede mo rin tawagin na driving force. And because of the fluid properties, so yung viscosity niya, nagkaaroon ka dito ng resistive force. Or yung viscous force ka na tinatawag. Okay, so let's proceed with this next slide. So, discuss lang natin kung paano ba na-derive yung equation na ito. This one. Okay, so dito pinapakita kung paano na-derive yung equation natin for Reynolds number. So again, coming from the definition, Reynolds number is just the ratio between the inertial force and the viscous force. So the inertial force, as we know it, that is equals lang sa force is equals to mass times the acceleration. Ayan. And the viscous force, so coming from our equation for the absolute viscosity or the dynamic viscosity denoted by mu. So that is equals lang sa shearing stress over dV over dy or the change in velocity with respect dun sa change in y. So if you're going to rearrange that and solve for the shearing stress, so ito yung magiging equation niya. So rearrange mo lang to. So shearing stress is equals to mu times dV over dy. And we all know, coming from our mechanics of deformable bodies, that shearing stress is equals lang sa force over the area. So if you're going to solve for the force, that is equals lang sa shearing stress times area. So if you're going to apply that in that equation for the Reynolds number, so Reynolds number is equals lang sa mass times acceleration over the shearing stress times the area. So alamin muna natin yung mga variable kung saan ba nanggaling to mga to. So assuming we have here a pipe, yan nga, meron nga dumadaloy na tubig dyan. So yung cross-sectional area niya, which is usually in the shape of a circle, so ito yung A niya, okay? And if you're going to get a specimen here to solve for the volume, so mamaya discuss natin kung saan nanggaling yung volume na yun. So kung alang na sample dito, again, since uniform naman yung cross-section niya all throughout the pipe, so eto, i-denote natin yung height ng iyong cylinder as L. So we all know that the volume for a cylinder is area times height. But for this example, that is area times L. And yung M natin, palitan natin into fluid property. So, i-relate pa natin yung M considering a fluid property. So, we all know that yung rho or the fluid's density is equals lang sa mass over volume. So, if you're going to solve for mass, that is equals lang sa rho times the volume. So, ayan. Substitute lang natin dito. Again, yung mass, naging equals lang dito, rho times volume. And yung acceleration, di ba, coming from our dynamics, acceleration is just the change in velocity over the change in time. So, kaya naging dV over dt ito. Okay? Over mu times dV over dy times area. So, again, ito is nanggaling lang doon sa formula natin for shearing stress. So, dito siya nakuha. Okay? So, ikinancel ko lang dito yung dV since common yung term na yun. So, maa-cancel na yan. So, ang mangyayari, our equation will now become rho times A, yung cross-sectional area mo nga, times L, or yung height ng iyong cylinder or yung specimen ng iwan natin to get the volume, is multiplied by the quantity of 1 over dt. So, sineparate ko muna siya times dy over mu times A. Okay? So, yung A, again, pwede mo siyang i-cancel. So, ang matira na lang sa iyo is itong nasa loob. But, yung dt natin, so alamin natin yung value ng dt. So alam naman natin na yung time mo will start at 0 and yung final time niya will be the time itself, t. So the dt, so if we're going to integrate that, that will be equals lang sa t minus 0 or yung dt pwede mong palitan ng value na t. Okay? And yung y, yung dy or the change in y, so, in order for us to get the maximum value of y, so di ba, yung y definition natin dito is ito yung vertical distance niya away from this axis. So, para makuha natin yung maximum value, so yung y natin can be denoted by the diameter itself. So, to get the y max, so that is equals lang sa diameter of the pipe itself or the inside diameter or the nominal diameter. So, again, if you're going to arrange that, so, ang magiging equation natin is rho multiply by the quantity of L over T and then times T. So, ito yun na. Sinubstitute na natin itong mga values na to. Over mu. So, alam naman natin yung L over T or this is just the distance over time. So, this is the velocity of the fluid itself. Okay? So, in short, ang magiging final equation natin, if you're going to arrange that using yung tip nga na tinuro ko sa inyo. So, our equation for Reynolds number, so, ano nga yung sabi ko sa inyo, tip? So, pwede mo siyang tandaan as magtanim ay dV rho, maghapong naka mu po. So, D, or that is the diameter of the pipe. V is for the flow velocity, or yung flow ng fluid sa loob. Rho is the fluid density, and yung mu is our absolute viscosity. So, check natin if tama ba na ang Reynolds number is a unitless Okay, so Reynolds number. So, palitan lang natin. So, ang diameter nga natin is in terms of meter. Yung velocity is in meter per second. Yung rho natin is the fluid's density, which is in kilogram per cubic meter. Over yung mu. So yung Pascal, i-expand ko lang. Saan nga equals ang Pascals? Di ba? Newton per meter squared and then multiplied by time. Okay, so if you're going to rearrange that, so i-cancel natin yung mga pwedeng i-cancel. So ito, pwede natin cancel and then ito, i-minus 2 lang natin so may matitirang isa. So ano pa ba? Yung second, pag tinaas natin, so pag ni-reciprocate natin, magiging per second squared. And then ito, so ito pwede mo nang cancel na ito. And then ito, mababawasan ng isa, so tataas. Or in short, ang ating magiging equation is kilogram meter per second squared over Newton. And alam naman natin na ito is equals lang din siya sa Newton. So the Reynolds number is in Newton per Newton, or again, this is a unitless. Okay, so we should take note that yung classification mo nga for Reynolds number can be divided into 3. So ano nga yung ating mga classification for Reynolds number? So Reynolds number can be classified as, so if the Reynolds number is less than or equal to 2,000, so this can be distinguished or classified as laminar flow. Okay? But if the Reynolds number is greater than or equals to 4,000, this can be classified as turbulent flow. And if the value is between the range of 2,000 up to but less than 4,000, so this is classified as a transitional flow. Oops! Tumaas. Basta transitional flow yan. Okay, so there's another version of this formula. Ngayon, if ang binigay sa inyo, if yung kinematic viscosity or denoted by the symbol, if kinematic velocity is given, so ganito yung magiging new equation mo para dito. So again, ang kinematic viscosity is equals lang do sa dynamic viscosity na mu over the fluid's density, mu over rho. Okay, so if you're going to solve for mu, so that is equals lang sa kinematic viscosity multiplied by the density. So again, knowing that yung equation mo for Reynolds number is dV rho over mu, ayan. So ito is pwede pa nating rearrange. So substitute lang natin tong mu. So ang mangyayari dito, so magiging dV rho over the kinematic viscosity multiplied by rho. So cancel mo lang yung rho, or our equation using the kinematic viscosity will be dV over the kinematic viscosity. Okay, so and lang yan. If given nga yung kinematic viscosity, just remember this equation.